Hello everyone, and thanks for being here today for this new seminar of from the IRENA committee. I'm Thibaut Dumont. I'm a postdoc in Strasbourg. I represent the KTEC infra part of the committee, IRENA committee. And so today we'll discuss about stellar physics. And I'm glad to have as a guest Shreeya Shetye, who will discuss about nucleosynthesis. So just to introduce her a bit to you. So Shreeya did her Master of Astronomy in Glasgow, in Scotland, before to achieve a PhD between Brussels and Leuven in Belgium, focusing on intrinsic and extrinsic S-stars in the Gaia era. Then she did a postdoc at the EPFL, so École Polytechnique de Lausanne in Switzerland, focusing on Cepheids, before to come back recently in Leuven in order to work on AGB stars. So Shreeya will discuss today about spectroscopic observations as tracers of stellar nucleosynthesis. And I can let you the floor now, Shreeya.
Thanks, Thibaut. Thanks for the introduction. I'll share my screen again. All right. You see my slides?
Yeah. It's okay.
And the slideshow?
Yeah, perfect.
Perfect. Okay. Do I start?
Yes, we can start. I will just specify that we'll take the question at the end of the talk.
Indeed. Yeah, I'll also start a timer meanwhile to get a little more control on how long I keep talking. All right. Thanks for the introduction, Thibaut. And indeed, as you heard already, I have been working a little bit on the stellar nucleosynthesis, in even more about AGB nucleosynthesis as actually in particular, which is all what we're going to talk about. This slide actually already has some spoilers, because you see the cartoon here on the right-hand side, which is an AGB star. My cartoon impression of AGB star, which is blowing these some elements in the interstellar medium. So we're going to understand this picture a bit better, but as we start talking about stars, I would like to actually set up the stage by mentioning about the evolution of stars, right? So stars with different masses evolve differently. And depending on at the initial mass of the star, if it is a small star, let's say like our sun, it will go through the red giant branch, and then a planetary nebulae die as a white dwarf. Can you guys also see my mouse? If someone can just say
yes, we
thank you. Thanks. So if it's a small star, just like our sun, for example, then it will go through these sets of evolutionary phases. And if it's a massive star, more intermediate mass or massive stars, it will evolve much more faster. And then, yeah, from a large, from a main sequence, quickly becoming a supergiant and then a supernova, and yeah, ending as a neutron star, as a black or a black hole, depending again on the initial mass of the star. This is a very simplistic picture of a stellar evolution, but it is just to give you a flavor that stars go through different evolutionary phases, and they die differently depending on what their initial mass was and what was the history during the stellar evolution. I guess it is clear to all of us kind of here within the IRENA community, I suppose, why we would be interested in the different phases of stellar evolution. Because most of the elements in the periodic table, they are produced in these different astrophysical sites. So to understand the origin of elements in the periodic table, different kinds of stars, depending on which is your favorite element from the periodic table, you could be interested in a different astrophysical site. My personal favorite are these dying low mass stars that you see here. So the stars we are going to talk about in this presentation are going to be these dying low mass stars, which produce these heavy elements you see here. And also they produce a lot of carbon and nitrogen. So these dying low mass stars, or AGB stars, asymptotic giant branch stars, they are responsible for the production of these heavy elements and for enriching these particular elements to the interstellar medium. Let's look at them more closely, again, going back to the cartoon that I was showing previously, the AGB stars, they lie somewhere here. So you can think of it as a second to last stage. So just before dying, ending up in a planetary nebula or a white dwarf, the low mass stars go through this phase called AGB. During the phase, how the structure of the star looks like. So you have this small core, relatively small core of the AGB star. Here we have an example for a 1 solar mass star. And then you have this extended loosely held envelope. This extended loosely held envelope is what is going to be your beautiful planetary nebula in the future. Now, if you focus more on the core of the star, you have a carbon-oxygen core, then there is a helium-burning shell, hydrogen-burning shell, and during the AGB phase, the star is burning helium or hydrogen in cycles. So is burning both, but in cycles, and again, the timescales of these cycles and all is also different. Then you have this helium-rich intershell. This helium-rich intershell is actually where all the magic happens. So let's zoom more into this picture. Here we are looking at the same structure of the AGB star, but from a different point of view. So in a different coordinate system. You have the mass coordinates on the y-axis. You can think of it also as a radial view. Basically, you're looking inside the star. And then the time here. So you have the carbon-oxygen core, which I already showed, the hydrogen burning shell, the helium burning shell, and then the intershell here, where I was saying that the magic happens. This helium intershell is the site for the S-process nucleosynthesis. For those who don't know, S-process is the slow neutron-capture nucleosynthesis. It follows the valley of stability, producing stable isotopes heavier than iron until lead. So everything from iron to lead is mainly produced by the S process, and AGB stars are the main contributors or the main sites for this S process nucleosynthesis. There are a few terms that I'm going to be using several times in my presentation, so let me introduce them to you. This blue region that you see here in this plot, these are called thermal pulses. Basically, the AGB stage is also called thermally pulsing AGB stage, because during the AGB phase, the star produces several of these thermal pulses, which are then followed by a mixing process. Each thermal pulse is followed by a mixing process. That's called a third dredge-up. So why is it third? Because the first and the second, they happen before AGB stages. We are interested in the third dredge-up. As the name itself suggests, it is dredging up material from the interior of the star to the surface of the star. So this is, you can think of it as some kind of mixing process. And these thermal pulses and third AGB, this kind of nomenclature I'm going to be using a lot in the rest of the talk. So AGB stars are main sites for S-process nucleosynthesis, and they produce the S process efficiently. They bring it to the surface, to their surfaces through the dredge-up process. And then towards the end of the AGB, or also a bit during the AGB phase, they undergo mass loss. This mass loss is responsible for introducing this whole nucleosynthesis history to the interstellar medium. Hence, AGB stars, with their strong mass loss, that's how they enrich the interstellar medium with this S-process nucleosynthesis material, and that's how we know, that's how we know that they are the sites for the S-process nucleosynthesis to happen. So again, this is a simple cartoonish picture here of the evolution of the star, where you have your 1 solar mass star, which from main sequence goes to red giant in your in the AGB phase. It also then loses this mass of nucleosynthesis material to the ISM, and then it dies as a white dwarf. If you had to convert that cartoon now to a more scientific picture, the commonly used diagram in stellar community to actually prove the evolutionary status of a star is an Hertzsprung-Russell or an HR diagram. In an HR diagram, we are plotting the luminosity of the star versus the effective temperature, and here you see tracks. So these are evolutionary tracks or stellar evolution models, you can think, for different solar masses, and you can see how the track evolves for 1 solar mass star, for example. From the red giant branch, you have the AGB here in pink. In the black the dashed line is the predicted onset of the third reg-up. So this is according to the models when the third reg-up occurs for the first time in these stars of different masses. And everything beyond this third reg-up, so everything beyond this dashed line should be AGB stage, right? Because after the third reg-up, after the dredging up starts, the star starts to showing signs of evidences of AGB nucleosynthesis, S-process enhancements, carbon enhancements, and so on. So this is the predicted or theoretical picture of AGB evolution. Now, if we want to probe this theoretical picture with observations, then the spectral class to look at could be the MSC stars. I mean, the M-type, S-type, and the carbon stars. S-type stars and carbon stars, they are in fact direct probes in a way, if you see, looking at their location, because S-type stars are located almost, or expected to be located almost where this predicted onset of third reg-up is. Then you have the carbon stars. Carbon stars, they have carbon enriched. So it's already clear that they are showing AGB nucleosynthesis evidence. And then we have the M-type stars, which are a bit less evolved counterparts, at least theoretically. This is clearly evident also from their spectra. So they show M-type stars and S-type stars show oxygen-rich chemistry. They are full of oxygen-rich molecules. These spectral classes are all cool stars. So they're much cooler than our sun. They are cool enough to host molecules. So you see either oxygen-rich chemistry or a carbon-rich chemistry, depending on how much carbon is already dredged up. So yes, these are all molecule-rich stars, and they evidently show the S-process enhancements and this kind of chemistry in their spectra. But there is a problem. So we know we could look at these stars to get get a better understanding of the S-process nucleosynthesis. And the problem while dealing with these stars just lies in this slide itself, that they are full of molecules. They are so cool that they host molecules, which makes the atomic abundance determinations very challenging, because you first have to get hold of this whole molecular veiling from, be it oxygen-rich molecules or carbon-rich molecules. It's equally challenging. So we want to have some probes or some tracers which would be a little less challenging than these molecule-rich stars. And these probes and tracers could be found if you think of or if you include a binary situation in the scenario. So now think or imagine that our star, our one solar mass star, has a companion. The primary year, the more massive one, will evolve faster, will go through the AGB phase, during which it might enrich the secondary with the S-process nucleosynthesis with carbon and all this nucleosynthesis history. And then you could look at the polluted main sequence star or the polluted red giant star, because that would be more easy to look at or to analyze, since they wouldn't be so cool and molecule rich. So basically, to probe the S-process nucleosynthesis, you have some direct tracers, which is of course directly the AGB star. But of course, the spectral analysis of the AGB star is challenging. And I'm going to give you a few more evidences of that further in my talk. We have some indirect tracers. These indirect or less evolved counterparts, they are excellent probes, because you could derive abundances for these stars, with better precision, without having to deal with molecules and so on. And I'm going to be talking about the direct and indirect tracers, both for the S-process nucleosynthesis. Now you have both direct and indirect tracers. They both are S-process enriched. So how will you know which of your stars are the direct tracers and indirect tracers? If we look back at the HR diagram again, which is our probe of the evolutionary status of the star, then clearly the direct tracers or the genuine AGB stars, they lie beyond this predicted onset of the third reg-up. And the extrinsic stars, or the stars which have been enriched with all the nucleosynthesis material because of a binary interaction, they are the less evolved counterparts, right? So they are here. So in an HR diagram, from an evolutionary point of view, you can clearly distinguish the intrinsic stars. So intrinsic here means by intrinsic processes. enriched by intrinsic processes, and extrinsic stars are stars enriched extrinsically because of a binary interaction. So through an HR diagram, you can directly segregate them in a way, the intrinsic and the extrinsic stars. Luckily, there's also another way of classifying these stars, and that's a more chemical way. And that way comes through technetium. Technetium is an S-process element with no long-lived stable isotope. And the only long isotope of technetium that you detect in these stars, its half-life is much smaller actually even than the AGB phase. So for the stars, for the genuine AGB stars who are constantly going through these thermal pulses and dredge-ups, fresh technetium is brought to the surface of the star with every pulse and every third dredge-up. And they show technetium-rich features, clear technetium-rich features in their spectrum, while the technetium-poor stars, they are extrinsic stars because they show enrichment in every other S-process element, but the technetium has already decayed because we are looking at the star way after the binary interaction has happened. So while when we are looking at them, the technetium doesn't exist anymore, but all the other S-process elements still exist. So technetium is a foolproof way of classifying your intrinsic and extrinsic type stars. And my favorite probes of the S-process nucleosynthesis, which was a focus during my PhD thesis, was these S-type stars. Mainly because I mentioned this already, right? The S-type stars are expected to locate where you predict the onset of the third dredge-up. So if you really want to understand the third dredge-up physics of when it occurs for the first time, basically, if you want to have observational constraints on this predicted line, then S-type stars are your go-to stars, basically. So they were the focus of my thesis, and they are going to be a focus a bit in the following few slides. What are the characteristics of these S stars? They all are molecule-rich. They show zirconium oxide bands and titanium oxide bands. They show also other kinds of oxygen-rich molecules, but zirconium oxide and titanium oxide are the dominating features. Titanium oxide bands you already expect in M stars already, but zirconium oxide, well, zirconium is an S-process element, so zirconium oxide, the presence of zirconium oxide is a kind of a sign that these stars are enriched with S-process elements as well. These stars are transition objects between M and C stars. I already showed this in the previous HR diagram. They have a carbon over oxygen ratio between 0.5 to 1. So the carbon is being dredged up slowly, but it is not yet high enough for the star to have a complete carbon-rich chemistry. So they still have oxygen-rich chemistry, they still have oxygen-rich molecules, and the carbon over oxygen ratio is between 0.5 to 1. So it's more than what you have for M stars, but less than still for a carbon star. We already know they all show in their spectra the presence of S-process elements, but not all of them make the S-process elements themselves. So they are intrinsic types and extrinsic types. Intrinsic S stars are the genuine thermally pulsing AGB stars. Extrinsic stars are the polluted binaries. And this distinction can be done thanks to with the help of technetium. So this is the basic characteristics and classification of S-type stars. What we want to achieve with the S stars is we want to locate them in the HR diagram, the evolutionary diagram of these stars. We want to mark the onset of the third dredge-up. We want to derive their abundances, right? These are the science questions we want to deal with. But to do all of this, you require a good handle on the atmospheric parameters of the S stars. And these atmospheric parameters, the parameter space is a bit larger than the usual one for stars in general, because here it's not only effective temperature, surface gravity, the metallicity plays a role for the S-process efficiency, then the S-process abundance itself and the carbon over oxygen ratio also is important. Now, if you want to solve this parameter space, then you need quite sophisticated tools, just because there's a huge degeneracy between these parameters. I'm trying to show this by giving you some example here. I'm comparing here two models, model A and model H. Model A has a certain set of parameters, model H has a completely different set of parameters. And at least it's not only within the region, wavelength region that I'm showing here, but also overall in the whole visible spectrum, it's difficult to disentangle which model, model A or model H, is the best representation of your observed spectrum. So it's difficult to say which one of them, it's difficult to choose, of course, not by eye, but even with any of the statistical methods, it's a little difficult to say which method is the, which model is the best representation and which parameters are a best representation for your star. And that's because of this strong entanglement or degeneracy in the parameter space. So we developed a kind of a routine which does this iteratively, and it solves for the 5 parameters that are mentioned here. And this tool makes use of Gaia as well as high resolution spectra and several several models as well. I will not go into the technical details of the tool, but I invite you to read if you want to. Yeah, if you're interested in the methodology, you could check out our papers. And also this has been validated on a several sample of S-type stars. So thanks to this method now, we can determine the stellar parameters of the S stars. And using the stellar parameters, you can do several things, right? First and foremost, you can again backtrack the evolutionary status of these stars. So on our predictions, which I have been showing already so many times, on top of that, I have overplotted the location now of the intrinsic and the extrinsic stars in this HR diagram. You have some peculiarities. So you have the intrinsic stars here beyond the predicted onset of the third dredger. This is nice. This is where we expect them to be. But you also have some extrinsic stars there. So we kind of are now in the process of reinvestigating them because we thought that there could be some errors on their Gaia parallaxes back then. We have to reevaluate this situation with Gaia DR3. So for now, I will ask you to just ignore them. The point that I want to highlight here is the following. So you have the predicted onset of the third dredger, which if you see kind of stops here at 1.4 solar masses or something. It's because the predictions or AGB models do not expect S-process and third dredger to occur for masses lower than 1.4 solar masses for sun-like metallicity. However, we saw direct evidence of technetium and other S-process elements in several S stars, which are almost 1 solar mass stars. So this is a discovery that low mass stars, like low mass as in the mass of the sun and the metallicity of the sun, can also produce S-process elements, can also go through third dredge-up. And this is an important feedback to the AGB models, but it's also interesting for us to know what could be the future of the sun, right? Like it could produce S-process elements. So this was an interesting discovery. And this is kind of, it also shows you that these confrontations between the models and the observations, how necessary they are, because that's how we learn what physics we need to be still input in our models. All right, so with the stellar parameters, you can not only locate the stars in the HR diagram, you can also then measure abundances. And we found several interesting things with the abundances. I want to highlight one problem here. So at the top, in the top panel is the carbon abundance, and the bottom panel is the carbon over oxygen ratio. And this is all plotted with respect to the S-process abundance. So it's like the average of the different S-process abundant elements. We have some predictions over plotted here, and some carbon stars, S stars and all. So actually, in principle, so S stars have a carbon over oxygen ratio less than 1. So in principle, the S-type stars, according to the predictions, should be only in this little square, should be located all here. But it is not the case, right? Because we have S-type stars also here, which have a high S-process abundance compared to the carbon over oxygen ratio. And these are stars which are just not predicted to exist. There's another way of looking at this problem. So let's pick up one singular case, the case of UISEN. Here, I have only plotted the predictions. So this just means how the zirconium over lanthanium over Fe, lanthanium abundance, or the C over O ratio is evolving with the pulse number. So with every pulse and with every dredge up, the star brings more and more of these material to the surface. So this is just how it is enriching, how it is evolving the abundance with every pulse. Now let's overplot the measurements on top of this. So of course, you have the measurements here for the C over O and for zirconium, lanthanum, but the shaded region is the error. Of course, the error on the observations is always a bit large. But what we have to focus on is that if you want to match the C over O ratio, the observed C over O ratio with the predicted one, then you need maybe 5 pulses to do that. But if you want to match the S-process abundances, the observed one with the measured one, then you need 10 pulses. In a simpler way, what I'm trying to say is that the predicted C over O ratio, it's increasing way rapidly compared to the S-process abundances. And this is the same problem that we saw also when I showed you the whole sample of S-type stars and carbon stars. So this is again another kind of tension between the models and predictions and the observations, which is nice, I like these kind of tensions because it's motivation to keep working and to adding more and more constraints on our models, but also improving the precision at which we can measure abundances with our observations. Now, there are some tensions and disagreements, but there are also some nice things. One of the nice results we found here during my thesis was with the zirconium and niobium abundances. So zirconium, niobium, both are S-process elements, but the monoisotopic niobium, which you find in the spectra of all these S-process enriched stars, that can only be produced by the decay of zirconium. So actually, for the intrinsic stars, which are your genuine AGB stars, there is not yet enough time for this niobium to be produced. So you expect them to have a zirconium over niobium greater than 1, because there's more zirconium which is not yet decayed into niobium. Whereas for the extrinsic stars, there has been enough time after the binary interaction for the niobium to be formed. So you expect a zirconium over niobium equal to 1. So this is all what you expect. And now if you see the figure in left, you have the predictions you have the models here overplotted with the observed abundances for intrinsic and extrinsic stars. So for the intrinsic stars do follow this nice track where they have zirconium over niobium greater than 1, and the extrinsic stars follow more like a unity trend. So apart from technetium, you could also use zirconium and niobium for the classification or distinction of this intrinsic and extrinsic, or your direct and indirect tracers of S-process nucleosynthesis. During this study, we found these 2 stars you see marked in blue. These are 2 stars which are technetium rich, and they show a zirconium over niobium almost equal to 1. We chose to call these stars bitrinsic, because they show qualities of intrinsic and extrinsic nature both. Actually, what we are looking at is the evolution of our polluted star. We are actually looking at the polluted star being now evolved itself in an AGB stage where it's producing the S-process elements itself. That's why we detect technetium. And it also shows history of its binary interaction with its former AGB companion. It's also nice to see the picture being complete and to also find these stars, which are kind of doubly polluted in S-process elements. And with this, we have found like the 3rd class subclassification of S-type stars, which you could call as bitrinsic stars. Before I wrap up the whole discussion on the direct tracers of AGB nucleosynthesis, I want to highlight some intriguing cases. And I want to mention some M stars. Now, again, to remind you all, M stars are not expected yet to show any traces of AGB nucleosynthesis. So they are not yet evolved enough, or thought to be not yet evolved enough in this MSC sequence. What we found is that not just we, but also some other authors have found that the technetium-rich M stars exist. So if we now look at 2 technetium lines, the technetium-poor stars, they don't show any absorption feature kind of. The technetium-rich stars show very strong absorption features. And then you have these M stars. So these are classified as M-type stars. They show TIO bands in their spectrum, and they show clear presence of technetium. So this is actually very interesting, because if these stars exist, it means that the real probes of the third dredge-up should be maybe the M stars and not the S stars, because they might be the first ones to show the traces of the third dredge-up. So we were very curious to locate these stars in the HR diagram. This is a preliminary HR diagram because this is still work in progress. So you have some of our technetium-rich M stars from our pilot study. When you plot them in the HR diagram, you see that they clearly have high luminosities. They are located beyond the predicted onset of the third dredge-up. They are located together in this region with the technetium-rich S-type stars. But what puzzles me is that how they show only technetium. Why do they not show zirconium oxide bands? Because if they would show zirconium oxide, then they would be classified as S-type and not M-type. So they show technetium, but not other S-process elements or not zirconium. And which is puzzling. Does it mean that technetium is kind of the first element to be produced and brought up? Or maybe these guys go through some kind of different S process, some different site for S process. I don't know. There could be differences in their S process profiles compared to the S-type stars. There are lots of open questions, and we are now working on a larger sample of these M stars. We recently got time for high resolution spectra for a large sample of these stars, and we are working on kind of populating this diagram with more technetium-rich M stars so that we can study their spectra and the S-process nucleosynthesis much better. All right, I think with this, I'm kind of done with my direct tracers of AGB nucleosynthesis. And I hope I've also given you a little flavor of the complication involved when you're looking at the AGB stars directly. Right, you have the molecules, you have your degenerate parameter space. So it's not that bad actually to go to the indirect tracers. Even if they are indirect, they still give you much easily a better idea on the S-process nucleosynthesis. So for the indirect tracers, you have several examples. I have already mentioned a bit about the extrinsic S stars, but you also have barium stars and some other classes as well. So just as the name suggests, what are barium stars? Barium stars are barium enriched. Barium is an S-process element, but they were classified as barium stars because they were strong barium lines, but they also show other S-process elements as well. So basically they are S-process enriched stars. Less evolved counterparts of the S stars we were looking at. So they are mostly here in the giant, you have the giant barium and the dwarf bariums. So these are less evolved counterparts, and they are much warmer. So they have a nice, beautiful molecule-free spectra where you can set up the continuum nicely and do your spectral analysis to derive the S-process abundances. Let me give you a quick view on what is the state of the art for the barium stars, what the picture looks like. It's kind of good because now they have done several high resolution studies for the abundance analysis for barium stars. The observed abundances match the nucleosynthesis predictions pretty well. I mean, within the error bars of the abundances. So the picture is quite nice and clean. There has been also a lot of effort put into long-term monitoring of these extrinsically enriched stars. So with long-term monitoring, you can also track the binary properties of the star. So basically what we want to do is we want to compare if the S-process enrichment is related to the binary property. So if the binary system is a wide binary, is maybe the secondary not as S-process enriched or compared to closed binary and so on. So we want to relate the binary properties of the system with the S-process enrichment we see in the barium star to kind of establish the relation with the binary system, that if there would be any. For now, the state of the art is that we don't find any such relationship because you see that there's a big kind of scatter over the full range. If you see individual elements here, individual S-process elements. So this is still ongoing, but I think the enrichment of S-process within the barium star, I think it's more related to the internal nucleosynthesis of the primary and the mass and the metallicity of the primary than the binary configuration. But this is still, yeah, I guess we need to expand the parameter space to be able to make much further conclusions. The other kind of extrinsically enriched stars, which are very thoroughly studied, are the carbon-enhanced metal-poor stars. And there's such a big diversity there, because you have the S, the Camp S, Camp R, the SR. Then you also have the carbon-enhanced metal-poor stars with no enrichment whatsoever of heavy elements. So it's a wide variety of these stars. And of course, this large diversity kind of gives you an indication that probably there are different enrichment sources. For example, the Camp S stars, they are believed to be metal-poor counterparts of the extrinsic S stars and the barium stars. So basically, they also have probably the S process enrichment because of a binary interaction with a former AGB companion. For the AR enriched, for the SR, there are different such scenarios. But this is a complete diverse zoo here. And the S process and R process, they are interesting, actually, very interesting stars to look at if you want to understand these S and R nucleosynthesis processes. It's also being debated and highly studied which element indices should be used. So which elemental ratios or indices should be used to best classify these SR and SRS stars. So here you have an example of this in the left, where the different color zones are different classification zones, basically, for the Kemp stars. And this is also studied much in detail, because depending on where they are located, then in such a plot, they could have different source for their nucleosynthesis enrichment. So I invite you to read all these interesting works by other people, because these guys are also interesting sites for the S process nucleosynthesis. One interesting evidence that they have found in these extrinsic stars is the presence or evidence of I process, or the intermediate neutron capture. I here, or the intermediate, stands for intermediate between the slow and the rapid neutron capture. So the neutron densities needed are, I think, in between them. And there has been evidence for this in the barium stars, and also they have used this as an explanation for the carbon-enhanced metal-poor SR stars. Now, what is happening is that you have some observations, measurements for the S process elements, R process elements, and those cannot be explained with an S only or R only model. So you need some kind of intermediate model to explain that. And here is an example of this blue line here, which then reproduces your complete abundance profile very well. So when you include S and R elemental abundances together. So this has been used to explain several such abundance profiles in these extrinsic stars. But so far, an I process to explain any abundance in an AGB star has been missing or not needed. It can also be that the AGB stars, maybe the errors at this point on the measurements itself are so large that they could fit any of the models, because as I told you, there are several challenges and complications associated with abundance determination for AGB stars. So maybe that's why we haven't felt the need yet to include an I process. But it will be interesting to keep following what happens here in the indirect tracers, and what kind of evidence you find here for the I process, and then try to see if such an I process also occurs. I mean, observationally is needed to explain the measurements for the abundances on AGB stars. Want to highlight that the source of this I process is also not yet completely understood or known. Also, the site of the I process is not known. I think I heard actually several talks within IRENA itself on the I process. So yeah, I think it is interesting. If you want to know more about it, then I invite you to listen to those talks for that. All right. It's almost impossible these days to give a talk without mentioning AI or machine learning or so on. We are in this era of large spectroscopic surveys where you have so many spectra, so much data available, at your disposal. And of course, we want to utilize these low to medium resolution spectra to determine S-process abundances, because this whole mass production or factory production of S-process can allow us to see different trends in the S-process nucleosynthesis, its relation to metallicity, for example. So in left here, I haven't plotted it. It's a figure from a paper from Norfolk, where they have used LaMost data to derive. So LaMost is medium resolution visible spectrum, to derive the abundances. And what is being plotted on the y-axis is the barium over strontium, which is kind of a proxy for HS over LS. HS, heavy S-process versus low S-process element, light S-process elements, sorry. So what is plotted in the y-axis is the heavy S versus heavy S divided by light S plotted against the metallicity. And it's been compared with predictions here and models in dashed and solid lines. And you see these kind of trends in the abundances or in how the S-process efficiency is evolving with respect to the metallicity. Now, what is happening is when you confront these machine learning abundances with high resolution studies, firstly, the high resolution studies are not yet as numerous, of course, because it's painstaking to firstly get the spectra, high resolution spectra, then do all the spectral analysis and so on. And so, of course, the high resolution studies are not yet available for the full range that these spectroscopic surveys cover. But you don't see these strong trends in the high resolution studies. Often the problem is also that the classification from these machine learning algorithms is incorrect. So for example, many stars which are classified as barium stars are actually not barium stars. When you look at the spectra, you don't detect the lines. The lines that they use, the spectral lines which are used in these machine learning algorithms sometimes are saturated lines, resonance lines, which shouldn't be used and which we completely avoid when we do detailed analysis. So my opinion for this is that it's amazing to be in this era where you have all these nice spectra to make use of. But I think we are still in the process of getting quite a lot of constraints from the detailed spectral synthesis, from the detailed high resolution spectral studies, so that we can have a good training set for our machine learning, for the current and the future machine learning algorithms. So I think for now, there are still some confrontational times basically between them. But soon, once we have large enough high resolution studies, to give a nice training set to the machine learning algorithms, I think the precision and the accuracy with the mass production of S-process in abundances will definitely increase a lot. All right, I think these are the little topics I wanted to touch. The general takeaway is that there are several direct or indirect tracers of the AGB nucleosynthesis. You could choose your favorite and you could choose the level of challenges you would want in your life. And then trace your AGB nucleosynthesis or the S-process nucleosynthesis. Both direct and indirect tracers, they kind of reveal some tensions between the models and the observations, which is good because it's a motivation to keep going and to keep gathering, improving the physics in the models and keep improving our observational constraints as well. And I think the confrontation with the machine learning with high resolution studies is a must. And that should be continued so that we can improve our methods and we can also improve this mass production of S-process elements. With that, I thank you for your attention and I'm open for questions.